In this video, we're going to go over lab exercise 4.2, which is to implement a 3-input prime number detector, but this time using a minimized form for our logic circuits. So what we're going to do is we're going to build a 3-input prime number detector, but we're going to use K-maps this time in order to derive both a sum of products and a product of sum minimized logic expression. And this is going to show us that we can implement the same type of logic functionality but using a circuit that has far less gates. And this results in using less parts on our board, making the circuit smaller, and also just consuming power and even running faster. So what we're going to need for this is a breadboard and wires, analog discovery. You're going to need your LED driver circuit from prior labs, and that should be on your breadboard already. It's going to require the slider switch, the 2 resistor arrays, 5 LEDs, and an inverter. So that should be already breadboarded. And then we're going to use a inverter IC, 2-input AND gate, 2-input OR gate, and then we're going to build these circuits. But then we're also going to do something toward the end, which is going to be kind of interesting, where we're going to interface our logic circuits to a magnetic buzzer. And this is going to require us to build a interfacing circuit because the buzzer actually will consume or draw too much current, and it'll draw more current than a basic gate can provide. And so what we need to do is we need to figure out how to interface that. And this is very common for logic circuits because you might do some computations such as determining whether an input is a prime number, but then in order to display it to the outside world, you might need to drive some sort of I/O that consumes more current. So it's very common to interface your small logic gates to larger devices. So we'll just take a look at an example interfacing circuit. Okay, so the deliverables are you're going to provide a design of your sum of products minimized logic circuit. Then you're going to demonstrate that on your breadboard. Then you're going to provide a design for your product of sum minimized logic circuit and then demonstrate that. So those are the first 4 deliverables. And then you're going to demonstrate the proper operation of a buzzer driving circuit. Okay, so the first step in this is to simply design the 3-input prime number detector using a minimized logic form. So what you're going to do is draw the truth table, and this is the same truth table as the lab 4.1, but this time you're going to put the information from the truth table into a K-map. And then from the K-map, you're going to derive the minimized sum of products logic expression. Now remember, when you do this, you're going to be circling groups of 1s, okay? And each group of 1 is going to be a product term in your sum of products logic expression. So what you'll see is that there's 2 groups that you can form. There's actually 3 you can form, but you don't have to do all of them. So what I would recommend is just do the 2 groups of 1s to cover all of the 1s in the K-map, and then you're going to OR them together, and that'll be a circuit. Once you get that logic expression, you're going to draw it all up. You will not have any fan-in issues in this lab because everything can be done with 2-input AND gates and 2-input OR gates. And then you're going to, in that logic diagram, you're going to draw rectangles around groups of gates that can be implemented with a particular IC in your parts kit. So what I want you to do again is I give you this piece of paper. Go ahead and print this out and draw out the truth table in this section. Draw your K-map right here, circle your 1s, and derive the minimized logic expression. And then draw the logic diagram right here. And then go ahead and do the mapping. So draw the rectangles around. You're going to need inverters. So go ahead and draw it around the 3 inverters for A naught, B naught, C naught. Draw it around. You're going to have two input AND gates. Draw a rectangle around that, and then write the part number that you'll use to implement that, and then draw a rectangle around the 2-input OR gate, and then write the part number you're going to use for that. And that's going to be deliverable number 1. So go ahead and take this piece of paper, either scan it or take a picture of it, and then that will be the deliverable for your design portion. Then you're going to breadboard it, and you are going to breadboard this. Go ahead and pull up any circuitry on your breadboard from before and go ahead and put it on your board. And what you're going to do is just like we did in prior labs, if you look at my breadboard here, you're going to have your LED driving circuit down here, and this is going to provide the 3 input codes or input bits, and then you're going to bring them up and you will implement a circuit here. Now my circuit is, yours is probably going to be a lot smaller than mine, but you're going to see inverters and then the AND gate and then the OR gate right here. And it's going to operate exactly the same as a canonical form, but just with less gates. So as I go through them, I've got A, B, and C here. It's 0, 0, 1, 0, 1, 0, and notice that the output is asserted. Okay, so I have it asserted for decimal 2, it's asserted for decimal 3, then we go to code 100, which is 4, it's not asserted. 101 is 5, it is asserted. 110, it is not asserted, and 111, it is asserted. So this is going to be a canonical sum of product, a minimized sum of products logic expression that's implemented on your breadboard, and you drive through it just like that. So take a short video of that, and that's deliverable number 2, showing the proper operation of your minimized sum of product circuit. And then you're going to do the exact same circuit functionality, but now this time using a minimized product of sums approach. So on this piece of paper that I provide, go ahead and draw the truth table again, just to have it readily available, and then derive the POS logic expression using the K-map. When you put the information into a K-map, remember for a POS, you're going to be circling groups of zeros. Now those zeros, you should see, you should be able to implement this using 2 groups, 2 circles, which will result in 2 sum terms. Okay, so you're going to have two input sum terms that will then go into a 2 input AND operation, and that'll create the product of sums logic circuit. So go ahead and derive that, come up with the logic expression for that, and then you're going to draw it out right here, draw the logic diagram, and then do the same thing where you map the logic gates into devices that you have in your parts kit. So draw rectangles around the 2 OR gates that you're using, and you should be able to put a part number next to that, draw a circle around the 2 input AND gate, and then that's your mapping. So to demonstrate your design process, go ahead and scan that or take a picture of this piece of paper, and that's going to be deliverable number 3. And then finally, go ahead and build that circuit on your breadboard and test it, and you should be able to get the exact same functionality as before. So then finally we come to the kind of part 5, or the 5th deliverable, and that is I want to create a circuit to interface to a buzzer. Okay, so if you look in your parts kit, there's this magnetic buzzer right here, and it's kind of a cool output device, and it makes a sound, and it's very simple. It's a DC single tone buzzer, and what that means is that you just put a voltage across its 2 pins, and it makes a noise, and it just makes a single tone. All right, you don't have to do anything, it just buzzes. Okay, now the way that this works is, if you look at this circuit, it has a plus and a minus pin, meaning that it's polarized. So it's similar to like a diode, where it's like you have to put the voltage across it a certain way for it to turn on. So what we're going to do is we're going to put VCC across this thing. So to the positive terminal, the plus terminal, we're going to go ahead and wire it up to VCC. And then if we put ground on this negative terminal right there, it would turn on. But we don't want it to turn on all the time. What we want to do is we want to have a logic gate control whether it's on or off. So what we can do is we can use this device called an NPN transistor. And you don't have to understand the operation of this. All you need to know is that when you put a logic 1 over here on this, what we call the base input to it, it will close this switch. So it acts just like a switch the way we're going to use it. And when you put a logic 1 right here, this terminal, which is called the collector, and this terminal, the emitter, will be, you can think of it as essentially shorted together. Okay, so it's a switch that is closed. When you put a logic 0 over here, the switch will open. So if you think about that, when the switch is open, this is a floating node right here, so it's basically there's no current flowing through it, there's no voltage drop across the buzzer, and it's off. So logic 0 means off. That's great. Logic 1 means the switch is closed. That means this is essentially a short down to ground, so VCC is driving current through the buzzer. There is a voltage developed across it, and it turns on. So that's wonderful. Okay, here is the trick though, okay? The buzzer takes 35 milliamps of current. So we can't just put like the logic gate right here to ground and have it drive it, because the output current specification on any of our HC74 parts or the 7400 series, it can only go up to about 25 milliamps. So if you try to drive the buzzer directly, it will blow out your part. Now the buzzer is interesting because when you put a voltage on it, it just takes 35 milliamps. It's like that's what its resistance looks like. And so this down here allows us to say, okay, I'm going to turn this on and off, but I'm going to have this separate circuit which is going to allow the current to flow through the buzzer to ground. And the great thing about this NPN transistor is it can take a lot of current. It can take like 200 milliamps, a huge amount of current relative to what we're talking about, before it is out of specification. But when we turn it on or off, it takes very little current into its control signal, which is coming in on this base, in order to get this switch to close and open. So it's going to take on the order of maybe a milliamp or less than a milliamp in order to turn this switch on. So this is a classic interfacing circuit. We want to use a control signal from a CMOS gate, which can only provide a tiny bit of current, but we're going to use that to turn on a switch that can or have a lot of current flow through it. Now, for the operation of an NPN transistor, you have to put a resistor right here in order to kind of limit the current that goes in there. So you're going to put a 10K ohm resistor in series between the output of the logic gate and the base. And then what you're going to do, there's another thing that happens that you need a diode for, and you don't need to understand this at this point, but what happens is that this is a magnetic buzzer. So as you turn it on and current starts flowing through it, it has a property called inductance, which just means that the current can't change instantaneously through it. So if you turn this on and it's buzzing and then you turned it off, the current would want to flow. Okay, it's going to flow for a little bit after you turn it off because it can't change instantaneously. It can't go from 35 milliamps to 0 in the blink of an eye. Well, I mean, it can't go, it can't turn off instantaneously. And so what happens is that when you turn it off, it'll force that current back into the transistor, and it'll actually damage it. So what we do is we put this diode here, and it provides it a path for the current to flow back into VCC in the situation that you turn the buzzer off. Okay, and like I said, this is something from circuits that you don't really need to worry about. It's just that this is a safety precaution right here. Okay, so that's the theory of this buzzer, and what you're going to do is you're going to breadboard that on your breadboard. Okay, so here's a drawing of it. I put the magnetic buzzer here. Remember that the longer pin is the plus side, and it's actually etched into the side of the magnetic buzzer. And then you're going to wire that to your VCC rails. Here's the diode. The diode is polarized, meaning that the anode is here and the cathode is here. That little gray strip is the cathode. And then what you do is you wire that down to the NPN, and the NPN, its pins are denoted using this bevel here. So you'll notice that one side is round, one side is going to be flat. So if you put it in your breadboard like this, you're going to have the collector up here, the emitter down here, and then this is what we call the base. And then you can take your 10K ohm discrete axial resistor and wire that here. And then you're going to bring in your control signal from the output of your prime number detector. So in addition to driving the LED in your LED driver circuit, we're also going to turn this buzzer on. And then of course you got a ground down here for the emitter, and that's the entire circuit. Okay, so let's look at my breadboard. So here is my buzzer circuit right here, and you can see I've got that on there, and transistor, diode, and the resistor. And I have my LED driver circuit going along right there. And so what I'm going to do is I'm going to go ahead and put a wire from here over into, let me turn this off first, so over into the input to that interfacing circuit, and it should turn on when I get to a code that is a prime number. So I'm going to turn on 3, and here we go. Listen to see if it turns on. Okay, it's on for 2 and for 3, but not for 0. So that's all we're doing really, is we just want to show another output circuit that is very common for a logic circuit. Now let me give you a little guidance. It's pretty loud actually, and there's a piece of tape on it. Don't take the tape off or it'll get really loud. So if I come along here and I take that tape off, let me see if I can get it here with this. It gets super loud. Here, I'm going to pull it out. I'm going to do this. So I should be able to grab that little piece of yellow tape. Okay, and I'm not going to pull it all the way off. I'm just going to get it so that that little opening in it is exposed. And I'll put this back in there. Listen to how loud it is. So if I put the tape on, it's loud and annoying. When I take the tape off, it's excruciating. Listen to how loud that is. So anyway, you're not going to want to leave this on for very long, but it does illustrate that you can interface a low current logic circuit to something that does draw a lot of current. And you know, buzzers are using a lot of things. I mean, they're using your phone, they're using almost anything. So anyway, okay. So after that, holy cow, let's turn that off. So I'm going to yank. Okay, so here we are. You have wired that up. Go ahead and test that thing. Take a video of it showing it on and off using your logic circuit to drive it. You know, and the video can be 2 seconds. And then you've done it. So after completing this lab, if somebody came up to you and asked you, could you design and implement a minimized sum of product circuit from a word description? Could you do it? The word description being a 3-input prime number detector. Could you write a truth table, do a K-map, create the logic diagram, and implement it with parts in your parts kit? Could you do the same thing using a minimized product to sum form? And then finally, could you describe the operation of an interfacing circuit for a magnetic buzzer? Could you just kind of tell somebody why you couldn't drive a buzzer directly with a logic gate in our parts kit and why you needed to use an interfacing circuit? And could you kind of describe the operation of that interfacing circuit, the whole notion of turning on a switch in the form of an NPN transistor? If you can, you have completed this lab. All right, we're done.